Okay, so for number 6, we have non-potable waters being pumped into a processing center where the depth in feet of the water at time t in hours is given by y equals h of t. Interpret the following statements. So h of 7 is 5. So that's how, okay, no derivative here. This just says, so remember, let's just decide. H of t is equal to the depth of water. And go for your units in feet, right? Okay, at time t. So we can say after 7 hours, time is in hours, the depth of the water will be 5 feet. Sounds good? All right, now this is a derivative. And so it's saying the rate of change of the depth. So we'll just say after 7 hours, the depth of the water is the word increasing because it's positive at, a rate of 0.6 feet per hour. So you got to use your units. I should have put that here maybe because it looks better. Okay, now we're on to the next one. Okay, I have the inverse function, no derivative, so this is just the other way around. This says, okay, when the depth is 7 feet, it has been 9 hours. So, or the depth of the water is 7 feet after 9 hours. Somehow, that's what you're just saying. You're just reversing these two, right? And so now I'm doing the derivative of the inverse. So, I have to say, when the depth of the water is 7 feet, okay, it will take 1.4 hours to rise 1 foot. So it's like you're going down to your units when you're doing that, to say it in reverse. All right, let's look at number 7. This is our first problem. That was all just trying to tell you and explain about the derivative, and I think it's very beneficial. It's going to help you in the long run. So we have a population, this is right out of your textbook, of killer bees that's migrated to a town in the Midwest. Yikes. Suppose the population P of killer bees in the town at time T in weeks. So we have the population, so bees is the population unit, and then T is in weeks. Okay, so you got to remember that. And it can be modeled by this function, which is a logistic function. Remember this logistic function? Okay, so it just asks us some questions. Find the initial number of killer bees that migrated to the town. So initial would mean that T equals 0. So P of 0, if you just do the math, you can do it because this becomes e to the 0. So you have 1,200 over 1 plus 39 e to the 0, which equals 1,200 over 1 plus 39 times 1, or 40. So that's equal to 30. 30 what? The initial number of killer bees, so killer bees. So at the end, always go what to get your units. Okay, B says, how many killer bees on the town after 1 week when T equals 1? So you just put in T equals 1 it goes on to say, find and interpret the rate of change in the killer bee population at t equals 1. So this is just putting t equals 1 into it, the first one, but then it wants the rate of change at t equals 1, so it wants you to take the derivative. It wants the instantaneous rate of change at t equals 1. So first let's find t of 1, and we're probably going to need our calculator for this. This would be p of 1, which is equal to 1200 over 1 plus 39e to the negative 0.24. So if you punch that into your calculator, and I really think you should do this computations when I talk about them on the video, because you have to practice using your calculator. We don't do it that often, and so you really got to get a little practice. So if you put that into the calculator, you should get 37.881, and remember we always go to 3 digits, so look at the fourth one to get the rounding right. 37.881 killer bees after 1 week. Okay, so that was just t of 1, but now we need p, so we want dp dt at t equals 1. Okay, so we have to take the derivative of p of t. And so I'm going to rewrite this 1200 times 1 plus 39e to the negative 0.24t. Okay, to the negative 1. Don't forget that. So this is going to be, this is just a rewrite. Okay, so probably should erase that. That's just p of t. So dp dt at t equals 1 is equal to the derivative of this. So it'd be negative 1200, right? Negative 1 going in front of the 1200, and then times 1 plus 39e to the negative 0.24t to the negative 2. And then we have to take the baby. So that'd be times 0 plus 39e to the negative 0.24t. And then we have to take the baby of this times negative 0.24. Now, since you're just using your calculator anyway, if you punch that into your calculator, you get how many, what's the rate of change of bees? You get, let's see, put 1 in, so you're going to stick 1 in. So you would get 8.804 bees per week. Okay, so what does this mean in relationship to, it says interpret the rate of change. So you can't just ignore that request to interpret it. So you would say after 1 week, remember how I do it, after 1 week, the population of killer bees, and we're talking about a rate, is increasing at a rate of 8.804 bees per week. Okay? All right, so now it goes, how many killer bees are in the town after 20 weeks? So you go back up to P of 20 here, and so if you do your calculator, P of 20 comes out to be 908.430 bees. So after 20 weeks, there's 908 killer bees, which, can a killer bee kill you? Because that's too many bees for me. Okay, so then they want P prime of 20. They want the rate of change. So P prime of 20, you would go right back here to your derivative and put 20 inside T. So T equals 20. And you should get, do that with your calculator, 52.974 bees per week. So what does that mean? Okay, so we're going to do the same thing. We're going to say after 20 weeks, the population of killer bees is increasing at a much higher rate, at a rate of 52.974 bees per week. Okay? So, yikes. All right, I'm going to stop this video there.